Picture a loaded truck rolling slowly through a car park and a small car speeding down a motorway. Which one is harder to bring to a stop? Your instinct might say the truck because it's heavy, but the car is moving much faster. Stopping difficulty depends on both how heavy something is and how fast it's moving, not on either one alone. You already know two quantities that describe how something moves. Mass, measured in kilograms, tells you how much matter an object contains. Velocity, measured in meters per second, tells you how fast it's going and in which direction. These are the exact two ingredients we need to solve the truck and car puzzle. Think about real experience. A heavy lorry crawling along feels hard to stop, and so does a light sports car screaming past. A slow, massive lorry and a fast, light car can feel almost equally stubborn to bring to rest. That suggests mass and velocity aren't acting alone. They're combining into some single measure of how much motion an object carries. So, how might mass and velocity combine into one number? You could add them or multiply them. Try this. If you double an object's mass, its motion should feel twice as hard to stop. Adding wouldn't reliably give you that, but multiplying would. Physicists settled on multiplication. This combined quantity has a name: momentum. Momentum, given the symbol P, is defined as mass multiplied by velocity. In equation form, P equals m times v. It's the formal answer to our opening question, a single number that captures both how much stuff is moving and how fast. Let's unpack every symbol before we calculate anything. P is momentum, measured in kilogram meters per second, or kgm(s) to the minus 1. M is mass in kilograms. V is velocity in meters per second. Because velocity has a direction, momentum does too. It's a vector, always pointing the same way the object is moving. Try a concrete case. A car of mass 1,000 kilograms travels at 15 meters per second along a straight road. What's its momentum? Substitute into P equals mv, P equals 1,000 times 15, which gives 15,000 kilogram meters per second. That's the car's momentum, a specific, calculable quantity, not just a vague sense of a lot of motion. Here's a trap worth testing. Suppose you think speed alone decides momentum. Picture a 5-kilogram bicycle and an 80-kilogram motorbike, both moving at exactly 10 meters per second. Same speed doesn't mean same momentum. The bicycle has 50 kilogram meters per second. The motorbike has 800. Mass matters every bit as much as velocity does. Now picture two lab trolleys on a track, moving toward each other, about to collide. Before they touch, each carries its own momentum, calculated separately from its mass and velocity. What happens to their motion the instant after they interact? Watch closely. Something about their combined momentum stays remarkably predictable. That predictable pattern is the principle of conservation of momentum. Provided no external force interferes, what we call an isolated or closed system, the total momentum of the trolleys before the collision equals the total momentum after. Motion isn't created or destroyed in the collision. It's simply redistributed between the objects involved. Picture a simple before and after diagram. On the left, two trolleys approach each other. each with an arrow showing its velocity. One labeled m1 v1, the other m2 v2. On the right, after the collision, new arrows show their changed velocities. The rule connecting the two halves of the diagram is this: the total momentum on the left must equal the total on the right. Let's calculate a concrete case. A 1 kilogram trolley moving at 3 meters per second collides with a stationary 2 kilogram trolley, and they stick together. Total momentum before the collision? 1 times 3 plus 2 times 0, which gives 3 kilogram meters per second. After sticking, the combined mass is 3 kilograms, so the shared velocity is 3 divided by 3, exactly 1 meter per second. Now try this yourself. A 4 kilogram trolley moving at 2 meters per second collides with a stationary 4 kilogram trolley, and they stick together. What's their shared final velocity? Total momentum before is 4 times 2 plus 4 times 0, which is 8 kilogram meters per second. Combined mass is 8 kilograms, so the final velocity is 8 divided by 8, 1 meter per second. Momentum doesn't change by accident. Something has to cause it. When a force acts on an object for some length of time, it changes that object's momentum. This combined effect of force and time is called impulse, and it's the mechanism behind every speeding up, slowing down, or change of direction. Impulse has its own equation. Impulse equals F times delta t, and this equals delta mv, the change in momentum. Here, F is the force in newtons, delta t is the time the force acts for in seconds, and delta mv is the resulting change in momentum in kilogram meters per second. A bigger force or a longer time produces a bigger change in momentum. Consider a 0.5 kilogram ball whose velocity changes by 8 meters per second over 0.2 seconds. What force caused that? The change in momentum, delta mv, is 0.5 times 8, which is 4 kilogram meters per second. Rearranging the impulse equation, F equals delta mv divided by delta t, 4 divided by 0.2, which gives 20 newtons. Here's a deeper way to think about force itself. Rather than just a push or pull, resultant force is defined as the rate at which momentum changes with time. How quickly an object's momentum is being altered. The faster momentum changes, the larger the resultant force needed to cause it. This gives us F equals delta P divided by delta T, where delta P is the change in momentum and delta T is the time over which it occurs. Notice this is just the impulse equation rearranged, and for constant mass, this reduces to the familiar F equals ma, the same relationship you've used before, seen from a new angle. Pause here and check your memory without looking back. Can you state momentum as P equals mv, impulse as F times delta t equals delta of mv, and resultant force as F equals delta P divided by delta T? If any of those felt shaky, that's useful information. Go back and firm it up before moving on. Now apply this to something surprising: car crumple zones. In a crash, a car's momentum change, delta P, is fixed by its mass and how fast it was going. But F equals delta P divided by delta T means that stretching out the collision time reduces the force experienced. Crumple zones extend the time of impact, so for the same momentum change, the force on the occupants drops. Bring it all together. Momentum, P equals mv, describes how much motion an object carries. In an isolated system, total momentum before an interaction equals total momentum after. Nothing is lost, only shared out. And whenever momentum changes, it's because a force acted over some time, following F equals delta P divided by delta T, which is delta mv divided by delta T. Next time you see a collision, from a snooker ball to a spacecraft, check what's conserved, what force acted, and for how long. That question, checked against these three equations, will carry you through almost any momentum problem this course throws at you.